The AP1 S2000, Honda's peak expression of purity in a performance offering, proudly produced from 1999 to 2004. So iconic, so revered that it's become a staple in games like Gran Turismo 4, and it's got such a big cult following, probably from Fast and Furious, that clean examples have now skyrocketed in price, especially during COVID. Lightweight, front mid-engine, rear-wheel drive, and a powertrain that sends shivers down anyone's spine when you hit VTEC as we just did there. This powertrain is so insane that this engine's basically the highest revving 4-cylinder from the factory in the last 50 years, revving all the way to 9,000 RPM, and the gearbox is revered as one of the best ever. And you know what's crazier? It made the most horsepower per litre at 123.45 until the Ferrari 458 Italia came along. That's right, a supercar had to dethrone it. So this little F20C that powers the S2000 AP1 and weighs less than 150 kilos is as race car of a 4-cylinder engine as it gets. And to fully realize the engineering genius behind the AP1 S2000, we're gonna conduct an automotive X-ray and dive deeper into what makes this car one of the greatest attainable sports cars of all time. Each section of this video has been divided into either the engine, gearbox, dynamics, suspension, or the chassis and underbody. So without further ado, let's begin on why everyone wants a S2000, the engine. Let's first get the basics out of the way. The F20C is a 2-litre aluminium alloy inline-4 which produces 247 horsepower at 8600 RPM and 203 Nm of torque at 7500 RPM in Japan, and 237 horsepower at 8300 RPM and 210 Nm of torque at 7500 RPM in the rest of the world. Why does the JDM version make more power, you ask? That's because it has a higher compression ratio than the rest of the world at 11.7 to 1 compared to 11.0 to 1, and high compression ratios allow the same combustion temperature to be reached with less fuel, whilst giving a longer expansion cycle so you get more power. This engine is also placed at the back of the engine bay to put as much weight as possible to the center of the car so that the car has a low polar moment of inertia, giving the vehicle quicker and sharper rotation and turn-in. The engine block is a one-piece, open-deck, aluminium alloy die casting, as well as fiber-reinforced metal cylinder liners, and using this material allows for lower weight, faster heat transfer, and less wear and tear over time when compared to conventional ferrous metal liners. The engine is a slightly over-squared design that has an 87mm bore and an 84mm stroke, so that's why there's so much power on the high revs, which we'll get onto later. When you have high revs, you need pistons that are very strong so they can handle the load. So Honda have done exactly that by using, for the first time ever in a Honda production car, high strength, lightweight forged aluminium pistons that are 355 grams each, with the piston's minimal skirt area contributing to less friction. The connecting rods are carburized and each weigh 636 grams, and the crankshaft, which are also steel forgings, are heat treated for added toughness. A high revving engine needs lots of rigidity, so it can stand the test of time, and with the F20C using large ladder type cast aluminium stiffener with cast iron bearing inserts which runs the full length and width of the lower engine block, they've done just that. This emphasis on engine rigidity continues through the use of a cast aluminium oil pan to help dissipate heat. Cast aluminium as a material also reduces NVH compared to your traditional steel stamp pan. Let's talk about the dual overhead camshaft cylinder head before we get into the juiciest part of this engine that justifies why many people seek this coveted automobile. Like this engine block, it's an aluminium alloy die casting, with the combustion chambers shaped into a pent roof with 4 valves for optimum high RPM airflow, and the valve springs, they are a single element round profile type which are a high RPM design borrowed heavily from Honda's race engine building experience. Now, onto the juicy bit. VTEC! It's used on both the intake and exhaust valves through packing the maximum amount of air and fuel into the combustion chamber on each intake stroke and then releasing the maximum amount of exhaust gases on the exhaust stroke. Each intake and exhaust valve uses two different cam load profiles, one for low RPMs and one for high engine RPMs. From idle to around 6,000 RPM, the two intake and exhaust valve cam followers at each cylinder are operated by low RPM cam lobes. And at this 6,000 RPM mark, you get this VTEC just kicked in yo feeling, where the ECU will tell a spool valve to open and send oil pressure to pins in the cam followers. Here, the pins lock the two intake valve followers and the two exhaust valve followers to a third follower, and now the car stays in VTEC until you go below 6,000 RPM. Let's just replay that VTEC kick, shall we? For the rocker arms and coaxial VTEC cam followers, which use roller element bearings, Honda have used a newer powered metal injection molding process, not only for better high production efficiency, but also consistent quality control compared to the older casting and machining methods they have used. This change alone has reduced valve train friction by approximately 70% and improved engine torque by allowing the valve train changeover point to be set at a relatively low 5,850 RPM. Let's now dive deeper into the oiling of the F20C. The two overhead camshafts are hollow, so that oil is supplied to the cam lobes for lubrication, and by doing this, Honda didn't need to implement a separate oil line and nozzles. And to help minimize engine length so that the engine is pushed as much to the back of the engine bay as possible, the oil pump was placed on the side of the engine block instead of its usual location at the front of the crankshaft. And with this change, the oil pump scavenges oil more efficiently. Placing the oil pump lower than usual also helps pressurize the lubrication system more quickly during engine startup. The oil pump itself uses a smaller, higher speed rotor and suction pickup ports on both sides of the pump body, and the pump is driven by a silent chain connected to the crankshaft. With the engine placed all the way at the back of the engine bay, Honda engineers decided to place the entire intake system in front of the engine, where the system can draw cool air directly from in front of the main forward engine compartment bulkhead. And since the system does not sit on top of the engine, the hood is lower, meaning better visibility. Now, specifics on the intake system. It consists of a large 5.5 litre expansion chamber, a low resistance conical axial flow air filter, and a main resonator. From the air filter, intake air flows in a short direct path to four large section tuned intake runners, and these runners, along with the cylinder head intake ports, have been carefully angled to provide the shortest, straightest airflow path into each cylinder. Until 2006, midway through the AP2 S2000's production years, Honda used a cable throttle body, so you get incredible throttle response and no rev hang, unlike the drive-by-wire that the overwhelming majority of cars use nowadays. What does an engineer love? Is it power or is it efficiency? In an ideal world, the answer is both, and Honda definitely killed two birds with one stone here. This is as Honda designed the F20C to also be a low emission vehicle engine by installing a high flow metallic honeycomb catalyst and a secondary air injection system. An ECM controlled electric air pump feeds fresh air into the exhaust secondary air injection system, allowing for the catalytic converter to heat up fast, which is a thin-walled, low-heat radiating metal honeycomb design in place of the more traditional ceramic unit. And this not only increases the exhaust gas processing surface area, but also heats up quicker, reducing hydrocarbon emissions when the F20C warms up. Let's dive deeper into the exhaust system for the S2000. It's a low restriction, high efficiency exhaust system, with the exhaust manifold using large diameter stainless steel tubing, and is a 4x2x1 design that flows gas efficiently. And the design choice of using a pre-chamber and two main silencers that utilize a U-turn pipe arrangement further reduces back pressure, and too much back pressure is bad, as that means less power. The heat shield for this is actually held by a metal strap that surrounds the manifold, and alumina insulators are attached to the back of the engine to help reduce NVH. So it's quite clear now that this is one of the best engineered engines ever, but we need something that allows it to operate at its best at any speed. So let's now talk about the slick shifting transmission. Before we delve into the gear ratios, let's touch on the technicals when it comes to this transmission, which is mounted longitudinally, with all 6 manual gears in reverse on 2 parallel shafts. By coupling both transmission shafts at the output end, Honda has reduced the load on the gear synchronizers by as much as 40%. Not only that, but shift loads are also reduced, making shifting easier. The transmission shift linkage is mounted on top of the transmission case, so you don't get any shifter slop. And shift throws are short and direct, which can be a double-edged sword, as many owners have reported that it is easy to misshift on the 6-speed manual. For the shift lever, Honda have used aluminium alloy end floats in a rubber mounting that absorbs vibration, and their race engineering shines through the S2000 manual transmission using its own lubrication pump, driven off the transmission's secondary gear, and this pump ensures that gears and synchros last long. Speaking about the synchros, there are double cone designed for first, third and fourth gears, and triple cone for second gear, and these all help reduce shift effort. Reverse gear meanwhile uses single cone synchronizers to reduce NVH. For the clutch, Honda engineers opted to use a pull type clutch mechanism and reinforced friction materials better suited to the high RPM nature of the powertrain. Of course, when you have 247 horsepower at the rear wheels, you need a type of diff that can put the power down without wheel spinning, and Honda have done that through adding a clutchless torsion limited slip differential which automatically transmits drive torque to the wheel and tyre with the most traction. But how does the power get transmitted from the differential to the wheels? By using a set of rigid one-piece axle shafts, the powertrain now has quicker throttle response on top of that cable throttle body we touched on earlier. Let's now have a brief look at those gear ratios. First gear is very long compared to even cars like a Honda Fit, and this is as the car has a 9000 RPM redline. However, the rest of the gear ratios are actually spaced closely together, so even when shifting in second or third, you end up staying in VTEC. The bigger final drive of 4.10 also significantly helps with this. However, as the ratios are so close, with 6th gear being a tad short of 4 final gear, your highway RPMs will be quite high. Of course, no one buys a S2000 as a motorway mile eater. They buy one to take it on the racetrack. And with that, let's focus on what makes this car so special around such corners: its dynamics. We already know that S2000 can go straight and hit VTEC, but how can it turn through the twisties? By steering. So let's cover that then, shall we? It's an electrically assisted rack and pinion setup like the Honda NSX, and while loads of reviewers have remarked the steering lacks feedback, opting for an EPS rack not only saves weight as you don't need a hydraulic pump and hoses, but the issue of leaking power steering fluid is practically eliminated, something that's actually quite a common issue on the Acura RSX. The electric motor that provides the assistance is microprocessor control and provides more assistance at low speeds and lesser high speeds. As the faster you go, the more your tyres load up, meaning your steering naturally gets heavier anyway. Honda have engineered the steering rack to have a very direct steering ratio at 13.8 to 1, and with steering kingpin and caster angles also optimized, not only do reviewers say the S2000 steering weighs up well in the corners, but it's also quite a fast steering rack. So the S2000 can accelerate, but how can it decelerate? Through using 4-wheel cast iron disc brakes, which are 11.8 inches at the front and 11.1 inches at the rear. The front rotors are also vented for added cooling, while the rear discs are solid. The brake calipers are also cast iron and are highly rigid and large, with the front piston diameter being at 54mm and the rear pistons at 40mm in diameter. The pad material is a high performance fade resistance type, with the brake pad area 42 square centimeters for the front pads and 27.9 square centimeters for the rear brake pads. To help you brake, Honda has used a 7.8 inch single vacuum servo assist unit to offer the best balance between pedal feel and assist. And the braking bias front to rear has also been optimized so that the front and rear brakes operate at maximum braking efficiency during heavy braking. In terms of the wheels, they are an open 5-spoke pattern. They are 16 inch x 6.5 inch for the front and 16 inch x 7.5 inch for the rear, and are made of lightweight aluminium alloy. Another important thing to note is the front and rear tires being different sizes, with 205/55 R16 89W at the front and 225/50 R16 92W at the rear. This is a staggered wheel and tire setup, and in powerful rear-wheel drive setups, these setups are almost always used, as wider rear tires help put down the power more effectively. Let's now move on to the quads and hammies of the S2000 AP1, the suspension. All S2000s use a highly rigid in-wheel double wishbone suspension all around, consisting of upper and lower wishbone arms at each wheel, with coil-over spring/damper units and NZ roll bars. For the wishbone arms, they're made of ductile iron and are connected to the body through special rubber bushings, which are designed to minimize vibration without compromising suspension rigidity. Double wishbone setups compared to more traditional McPherson struts or torsion beams are great, as you get what we call Kemper gain, which is essentially when the suspension is compressed, the wheels slant inwards a bit more. With this in mind, Honda didn't need to run huge amounts of static negative camber from the factory, only running a mild -0.5 degrees at the front and a slightly more aggressive -1.5 degrees at the rear. Ball jointed lower arms have been used to increase roll stiffness, as well as a 1.11 inch diameter front stabilizer bar and a 1.07 inch rear bar, which helps the S2000 corner quite flat, and the bars connect to their respective suspension arms via ball jointed links. To reduce this body roll even more, the S2000 uses monotube shock absorbers instead of a twin tube setup to not only corner more neutrally, but also feel stable at high speeds. However, at the trade-off of a slightly stiffer ride, as you do have more gas pressure in the shocks than you do with twin tubes. Attached to the lower wishbone arms are rear dampers, which feature large remote reservoirs, leaving more space available for the folding soft top and space saver spare tire. Unfortunately, however, when driving at the limit, the AP1 S2000 tends to suffer from a sensation that we call snap oversteer. This is as the rear suspension is designed to limit dive on braking, and when you either lose grip or lift off while that rear suspension is loaded up, the sudden weight transfer causes the suspension to decompress and then snap the rear end sideways. Fortunately, this is an issue that the AP2 S2000 solves, which we'll get into more detail for our next Automotive X-Ray. With that being said, let's now move on to the final but arguably crowning aspect of the AP1 S2000, the chassis and underbody. Let's start off with the weight. It's very light, weighing over 2,765 pounds or 1,270 kilos in AP1 trim. In terms of the styling, of course, it's one of the most beautiful JDM sports cars ever. If this was sold brand new in 2025, you'd definitely be fooling me. But its style isn't just form, but also function, with the hood line dropping away to a low, strong nose, shaped for minimal aerodynamic drag and good forward visibility. Say you're driving with the top down on a racetrack. What if you crash and your car rolls over? Well, the S2000's roll bars combined with the car's cantilevered windshield frame to help form a protective area for the drivers and passengers' heads. However, we always suggest a roll bar, and other S2000 and Miata owners will preach the same. As we found out earlier in the video, the short 6 gear means that this car does hum a bit noisier than the average consumer would like, so Honda have included vibration absorbing engine mounts and suspension bushings, resonance damping chambers in the intake and exhaust systems, and soundproof materials applied to the floor tunnel and trunk to reduce as much NVH as possible. With the front mid-engine setup, the weight distribution is a perfect 50-50. Before we discuss the legendary chassis this car offers, let's run through a quick demo to show you the engineering dilemmas faced by Shigeru Uehara and his engineering team at Honda when designing the AP1 S2000. Watch me twist this shoe block without a lid, and now watch me do it with the lid on. See the difference? The point is, open-top cars have a way floppier chassis, so with this in mind, Honda designed a monocoque body with a centralized backbone frame for the S2000. The backbone tunnel is enclosed by the floor and runs down the center of the cockpit, between the driver's and passenger seats. The large side seals provide extra strength, and the diagonally braced front and rear bulkheads tie the frame members together into a strong beam-like structure that resists bending and torsion forces. The cross members running under the driver's and passenger seats add extra stiffness, and the front and rear portions of the central frame and the side seals tied into diagonal X braces at the rear of the cockpit and at the front cowl, and these X members connect directly to the front and rear suspension subframes, so that's why it's often called the X-bone frame. Despite the front subframe's lightweight and compactness, its lateral rigidity is quite high, with the engine mount structure designed to reduce lateral movement in the frame when cornering. On the other side, the rear subframe is a three-dimensional structure consisting of hollow steel pipes that connect the rear side members and floor tunnel to the upper and lower arms of the rear suspension. A deep section rear cross member ties the beams together and anchors the rear of the differential. And this is where we'll end it off for the main engineering sections. The ethos about the S2000 was never about speed, it was always about the driving feel and sound. With that, let's now head into the concluding remarks. Overall, what are my thoughts on the AP1 S2000? It's simply one of the most exhilarating cars for the price, all while being rock solid in terms of reliability after almost 3 decades. If you've got any other cars you want us to conduct an automotive X-ray on, let us know in the comments. Thank you so much for the support already with the previous automotive X-rays. Let's keep this up so we can continue to make this a regular thing on YouTube, where we really break down and dissect some of the best cars ever. Much love to you all, and I'll see you in a bit.